This is section 7.2, the least square line. The objectives of this video are to define the least square line equation. Least square line in short is LSL, and we want to calculate the LSL parameters, define and assess how good is the fit of this line approximation to the data, and finally to predict new values based on the LSL equation. Examples and applications of the LSL approximation are to predict the height from edge, to predict the distance from wall from sensors, to predict the strength of composite materials, and in general in artificial intelligence, the goal is to estimate line parameters of training data or from training data. So we have XY pairs, and with those pairs we want to estimate the linear approximation of y with respect to x, and as we keep feeding with data, the model will start to improve and do better predictions. The first model is a zero order model, so let me write it down. Zero order model. So the objective is to collect data in order to predict the output of an event. Let's suppose that we have the concentration of a substance and it diffuses in a medium. So we measure different concentrations, 49, 55 and so forth. And the zero order model, it will give you just one value. So in that case we have that concentration is not a function, but is just a constant. So in this case, this is not a variable, but just is instance, is an index. So it's an index, and the way to predict the value, it will be just the mean. So in this point, so that will be the mean of the concentration. Let's say that. So y mean, y in this case meaning concentration, it will be equal to 1 over n multiplied by the sum of all the measurements that we have. And the error of this prediction, we can compute it by the value of the prediction, which is the mean, compared with every one of the single measurements that we have. So if we have this, it will be epsilon 1, epsilon 2, epsilon 2. So that will be the error in each single case, and so forth. We do for every one of those measurements, and we add them all. So the error will be equal to the sum of epsilon I. And remember that if we just take the distance, so this is a negative distance, and this is a positive distance. So if we add them all in that way, they will cancel out, because that's going to be the definition of mean. And we are comparing with the mean. So we need to make this either absolute value or square the result. So we are going to square this result. So it will add and won't cancel out. So the error is square. So that's the square in the least square, but we are going to get into the details. So in other words, the error is equal to the sum of x minus, and we are using y, so y minus y mean square, yi, and the sum of all over our data. Okay, let's move into a first order model. So for our first order model, we have two variables, and we want to find out the relationship in between time and concentration. In this case, the variable that we have control of is time, so we call this the independent variable. And the variable that we measure is the concentration, so that will be the dependent variable. And we want to find out the best line that approximates our data. So we want to find two things: the interception and the slope. So we have that concentration is a function of time, and so therefore we have that C as a function of time is equal to m, the slope, multiplied by t plus a constant. This is the slope, and this constant is the interception. The optimum line that fits the data. The equation of the line is y hat of x equal to beta 0 plus beta 1 of x. Beta 0 is the intercept and beta 1 is the slope. And this equation constitutes a model in the sense that it is able to predict the corresponding value of y given x. Now, from all the possible lines that we have, the one that we want is the one that minimizes the error. And the error can be measured as the distance in between the predicted value. For example, in this case we have xi, and this is the observed value, yi, and this is the predicted value, y hat of xi. So this distance is the error for one observed value, and we want to take the sum of all of them. The only consideration that we must have is that as some of them are positive and the other ones are negative, when we add them they can cancel out. So to avoid the cancellation, we can do either two things: we take the absolute value or we square the result. So the common practice is to square the result, and if we expand the value of the predicted with the equation, so we have that the error is the sum of yi minus beta 0 minus beta 1 xi squared. So we need to find beta 0 and beta 1 such as the error is minimum. If you remember from calculus, to find out the minimum, we can derive an equal to 0. So if this is the error, in this case epsilon, our equation is quadratic, so a quadratic equation will guarantee that it will have a minimum. We need to find beta 0 such as the error is minimum. So that's the value that we want for beta 0, and the same thing for beta 1. So we need to find beta 0 and beta 1 that minimize the error. Okay, let's find our optimum values for beta 0 and beta 1. So what we have to do is derive the error and equal to 0. So we are going to derive with respect to beta 0 and beta 1. So in the first case we have the derivative of the error with respect to beta 0 is equal to, and let me highlight, beta 0. So we have the derivative of this sum, which is equal to the sum of the derivatives, and we have a square term, so which is 2 times the term multiplied by the internal derivative. So in this case is the sum of 2 times yi minus beta 0 minus b1 xi multiplied by the internal derivative. So everything apart from b0 is a constant. So we have the derivative of this is 0, the derivative of this is 0, and the derivative of minus b0 with respect to b0 is minus 1. So that's minus 1. Now we have to derive the error with respect to beta 1. And let me highlight now where is beta 1. So beta 1 is there, and everything different from beta 1 is a constant, so these two are going to be a constant. So our derivative is the sum of 2 times yi minus beta 0 minus beta 1 xi, now multiplied by the internal derivative, and in this case it will be the derivative of just this term because these two are 0. So the derivative of this term with respect to beta 1 is minus xi. So minus xi. Now to find the minimum, we have to equal this to 0 and solve for beta 0 and beta 1. But let me expand the two terms before proceeding. So in the first case, we can simplify a little bit. In the first equation, we have this negative 1. We can cancel it out because we have a term that is multiplied by negative 1 is equal to 0. So one of the two is equal to 0 and minus 1 is not. It's the same case for 2. So 2 can be cancelled. So we have that. Apart from that, all of this term must to be equal to 0. And the same thing in the second case. So we can simplify the negative and we can simplify the 2, but we have to multiply xi by every single of these terms. So let's proceed in the first case. So in the first equation, we have the sum of yi. So I'm distributing the sum of each single term minus the sum of beta 0 minus the sum of beta 1 xi equal to 0. The second equation, we have to multiply xi by every single term, and remember that we can cancel the 2 and the negative. So we have the sum of yi multiplied by xi minus the sum of beta 0 multiplied by xi minus the sum of beta 1 multiplied by xi and multiplied by xi, that will be xi squared equal to 0. Now remember that our variables are beta 0 and beta 1, and we have to solve for beta 0 and beta 1. So in reality we have two equations and two variables, beta 0 and beta 1. Let's set up our system of equations. I rewrote the equations here so we can simplify them furthermore. In the first equation, we have the sum of yi minus the second term. We have the sum of beta 0, but the sums are from 1 to n, so we are adding n times beta 0. So this is n multiplied by beta 0. The third term, we have beta 1 multiplied by xi. So the sums are in I. So beta 1 is multiplying all of these terms. So we can factorize the beta 1. So minus beta 1 multiplied by the sum of xi equal to 0. Now the second equation, we have the sum of xi yi minus, we can also factorize beta 0 out of the sum. Beta 0 multiplied by the sum of xi. In the third term, we can also factorize the beta 1. So we have minus beta 1 multiplied by the sum of xi squared and equal to 0. Now remember, our variables are beta 0 and beta 1, and that should be beta 0 and beta 1. So I want to keep everything with beta 0 and beta 1 on one side of the equation and move everything that doesn't have beta 0 and beta 1 to the right hand side. So those are the independent terms. So to simplify things a little bit, I'm going to multiply by minus 1 the first and second equations. So this term is going to be moved positive or out to the right hand side and everything keeps the sign on the left hand side. So let me do it. Let's multiply by -1 all the terms. So we have minus, plus, plus. The second equation we have minus, plus, plus. Now I'm going to move this and this to the right hand side. So we have n times beta 0 plus beta 1 multiplied by the sum of xi equal to the sum of yi, and beta 0 multiplied by the sum of xi plus beta 1 multiplied by the sum of xi squared equal to the sum of xi yi. Now we can write or rewrite these equations in matrix form in the following way. Notice again that our variables are beta 0 and beta 1. So beta 0 is multiplying the first term and beta 1 is multiplying the second term. So the matrix of coefficient will be n and the sum of xi, and the second row will be the sum of xi and the sum of xi squared multiplied by beta 0 and beta 1. And the right hand side is the independent terms are the sum of yi in the first row and the sum of xi yi in the second row. So we can solve for this metric system, but we can notice that if we divide by n, it will simplify the first row a little bit nicely. So I'm going to divide by 1 by n. So by dividing the first row by 1 by n, this will be n divided by n is 1, and this is the sum of xi divided by n, and the sum of xi divided by n is equal to the mean of x. And the same thing with the last term, the sum of yi divided by n is equal to the mean of y. So let's rewrite the first row in that form. So we have 1, the mean of x. The second row, I'm going to leave it the same way, the sum of xi, the sum of xi squared. So we have beta 0 and beta 1, this one doesn't change, and the right hand side it will be the mean of y, and the second row doesn't change, the sum of xi yi. Now we can solve for beta 0 and beta 1, and I'll leave it up to you, but it's very straightforward. And when we do, we can find this for beta 1, and then we replace the value in beta for beta 0, and we obtain this value. This is an equivalent equation for beta 1, but this one is easier to compute, and is the one that you will obtain if you use this form here. Okay, so what we have got is that predictions for x can be computed based on our equation y of x equal to beta 0 plus beta 1 multiplied by x. Okay, what is important to notice is that we want to choose x in the data range. So if our values of x were in between 0 and 100, so we expect x to be in between that range and avoid values of x outside of the range, because we cannot guarantee that our line will approximate those values.